So again, we have a incoming beam. It's always with some wave vector k coming in some direction. You have a spherically symmetric potential, V of r. And then we're looking at the scattered particles in some direction k prime. And so the angle between k and k prime is called theta. And typically, if V is really spherically symmetric, you'll have a cylindrical symmetry because you only have an incoming direction and then everything else is spherically symmetric. So there's a cylindrical symmetry around the k direction, which we always say is proportional to z hat. That's kind of the convenient setup for the coordinates. And we spent some time looking at solutions to the Schrodinger equation. So again, this is still just a solution to, this is still just solving the Schrodinger equation. It's just for a particular kind of boundary condition, right? All we ever do in this class is solve either the time-dependent or time-independent Schrodinger equation subject to various boundary conditions. For scattering, the boundary condition is just that there's an incoming plane wave. So far away, the solution looks like an incoming plane wave plus whatever the stuff that comes out due to the scattering. So the general form of the scattering solution is just given by that, an incoming plane wave and a outgoing wave, which is convenient to express in spherical coordinates. So the solutions to the Schrodinger equation are labeled by the incoming momentum and far away for kind of distances, far away from, say the scale of this is like A for far away from the potential. The solution just looks like an incoming plane wave plus an outgoing spherical wave, which looks like that. So those are the solutions to the Schrodinger equation that we're interested in. Then we spent some time trying to understand the solution and how we can expand it using what we know about the Schrodinger equation. We know the Schrodinger equation has the following Hamiltonian. So we know that the Laplacian part, the kinetic energy in 3D, we should be able to diagonalize the angular part of it using the spherical harmonics. So that leads us to the partial wave expansion, where we expand things in terms of the Lm quantum numbers. And of course, the Laplacian just depends on the L quantum number. It's got a radial piece and then an angular piece, which is, the L plus 1 portion of it. So that's what we're doing. And last time, what we did is we expanded our solution in spherical harmonics, essentially, which for things with cylindrical symmetry, you end up getting just an expansion in the Legendre polynomials. It's just the PL of cosine theta part of the angular wave functions, the spherical harmonics. And in the end, we showed that this kind of form here, it can be expanded as follows, where psi, I don't know what's up with my pen today, psi of r theta, which again is for that spherical cylindrical symmetry. There's that constant out front. Then there's a sum over angular momentum modes. This is the partial wave expansion, 2L plus 1 minus 1 to the L over 2IKR. And then we have minus 1 to the L E 2I delta L. The delta L's are the phase shifts. And we have an outgoing spherical wave portion and then an incoming one. And all of this is multiplied by PL cosine theta. So this was kind of the result of analyzing the solution to the Schrodinger equation. How we did this is we looked at, so far away from the potential, you of course don't have a potential, it's 0. So you can look at the solution to Schrodinger's equation without a potential. And we looked at those solutions and they were Bessel functions. And we looked at what happens to the Bessel functions for large radii. And in that case, the Bessel functions reduced to their sines and cosines divided by R. And we used those to basically compare that solution to the one that we know we must have asymptotically, which is this one. And this I haven't proven to you yet that solutions to the Schrodinger equation have this form, but I will later. So by comparing the solution to the Schrodinger equation without a potential to this form, we're able to sort of match the different pieces together and rewrite our solution, in this form, where these various pieces came from expanding the plane wave in spherical harmonics, and we saw that the phase shifts are related to the expansion of this scattering amplitude in terms of the spherical harmonics. So I should probably write that down also as a kind of fundamental equation for the partial wave expansions, that the scattering amplitude as a function of theta, again, for things with sort of cylindrical symmetry, spherically symmetric potentials. So that the only thing that matters is the angle between the outgoing direction and the incoming one. That's equal to 1 over k sum L equals 0 to infinity 2L plus 1 E. Try to see if I can fix my pen. But yeah, any questions so far? Kind of just going over the important concepts, because we kind of just did the calculation last time, and I want you to understand why we did that calculation. Okay, so let me see if that worked. So the rest of it is I delta L, and then there's sine delta L, and then it's PL cosine theta. And of course, the scattering amplitude is related to the differential scattering cross-section, which is the actual measurable thing. It's just the square of this function. And you can then derive, and this you'll do on homework 4, this half homework, that the total scattering cross-section is 4 pi over k squared, sum over L, 2L plus 1, sine squared and delta L. So these are the major formulas. Again, the idea is this should be the asymptotic form of the solutions to the Schrodinger equation. We can then actually solve the Schrodinger equation. We get Bessel functions, then we can compare these two things and relate the general solution, which of course has two different coefficients in it because it's a second order equation. One of the coefficients was these phase shifts, delta L. And these phase shifts are the things that are related to the scattering amplitude there. And so all in all, we can connect the scattering amplitude to the phase shifts, which then gives us the scattering cross section. And the other important thing to note is that if the phase shifts all vanish and they only come in here in the solution, if all the deltas are 0, then this just becomes 1. And then you just get a expansion for the plane wave part. And these guys are called the S matrix elements for the Lth partial wave. And we'll talk more about those later. But in these guys, which again, everything depends on the incoming momentum. These guys are just the exponentials of 2I delta L, and the phase shifts themselves depend on the incoming momentum. So these are kind of the key formulas. So what we're going to do now is kind of go back and try to understand these formulas in terms of classical intuitions, because this is not so transparent. And we should try to connect it back to what we know about cross sections classically. So if we think about, so let's build some sort of classical intuition about these things. So what we have is we can imagine the Lth contribution to the scattering cross section, which would be 4 pi over k squared, 2L plus 1, sine squared delta L. So that's from the Lth mode in our partial wave expansion. That's what contributes to the total scattering cross section. And what you can notice about this, of course, is that this is bounded by 4 pi over k squared 2L plus 1, because the sine squared ranges from 0 to 1. So a particular L, of course, it corresponds to a particular angular momentum, right? That's just the quantum number for angular momentum. So we know that this L corresponds to some angular momentum, h bar L, roughly. Of course, you know, it's L squared and so on, but the magnitude of the angular momentum is h bar L, roughly, for like large L. So what it means is that this contribution, right, would come from a particle that's incoming at that particular angular momentum. And if you remember from classical mechanics, if you have a particle and there's some target with some origin, so this is the origin of the spherically symmetric potential, the V of R. If you have some incoming particle, its angular momentum is going to be related to the distance away it is from the origin of your coordinate system. And that's just the impact parameter, B. It's just how far away you are from the midline of the target. If you remember classical mechanics, I don't know, like freshman physics, you have an angular momentum associated with linear motion. It's given by the mass times the velocity times the distance you are away from the the origin. So that's what it is. So that means we are considering incoming particles that are shooting in here, or I should say, I should draw this up here. So this is the incoming particles coming in here at this impact parameter. It's coming in with a particular momentum. So this is equal to, right, a linear momentum times the impact parameter, which we know now is, h bar k. B is coming in with a particular k, and this is approximately equal to h bar L for this particular contribution. So if we think about that, what is the range of impact parameters corresponding to a particular L? Well, it must be everything that sort of corresponds to that that quantum number h bar, the quantized angular momentum h bar L. So the range of impact parameters, must be within at least some range between L and L plus 1. This is just from this formula here. So, classically, that's what you would have classically. So, quantum mechanically, we know that the angular momentum is quantized with this quantum number, but classically, if you were to think about the correspondence, what would happen? What range of impact parameters would correspond to that quantized angular momentum? It would just be whatever impact parameters are consistent with having that angular momentum, and it would be some range between corresponding to a range between L and L plus 1. That's the range of impact parameters you would have classically. And so kind of the maximum impact parameter you could have is, or rather the range that corresponds to is going to tell you something about the classical cross-section, right, related to that range of B's. Remember that for a range of B's, the impact parameter, what the particle sees as it approaches a target, say like a hard sphere or something, it'll see a kind of ring, right? Ring on the target that's of radius B, right? And it'll see, that's the amount of the target that it sees at a given impact parameter. So for a range of impact parameters here between some minimum and some maximum, say, B min and B max, the amount of area that the target particle sees classically. So this is the classical version of this L contribution. Well, the most it can see, of course, is going to be whatever it sees if there's just a hard sphere there. So the most it can see is that total area covered by this orange rim with, the radius ranging from B min to B max. That's sort of the most it can see. So the scattering cross-section is bounded by sort of the amount that it would see if your target was just a hard sphere, because you can't scatter more than just from a wall, right? An impenetrable wall. So that's kind of the most area it can be. So the classical contribution to the scattering cross-section has to be bounded by that area, which is just the area of that disk, or I don't know what you call it, the annulus. So it's the area of the disk, radius B max, minus the area of the disk, radius B min. And we know what these things are. It's just these guys, the maximum minimum values of the impact parameter for those L values. And look how nice this is, because we now sort of see it's very natural to have this 1 over k squared scaling here, and we see that this, if we expand that out, it's going to be pi times 2L plus 1, has really a very similar form as the quantum mechanical cross-section over k squared. But notice a very key thing. In the quantum mechanical version, we have a 4 here. And here we don't have a 4, we just have a 1. So that means that the classical contribution to the scattering cross-section is at most a quarter of the quantum mechanical contribution. This is a quarter of the possible classical maximum contribution. Sorry, the maximum quantum mechanical contribution, right? Which is this guy. This is the maximum contribution quantum mechanically. So it means that quantum mechanics sort of gives you more scattering than you would expect, because classically what would happen is if you had, the most you can get in terms of scattering is if you're just sort of scattering off of a hard sphere or something. And if your impact parameter is beyond the radius of your hard sphere target, then you know classically you can't get any scattering, right? Because the thing will just kind of shoot past the target, right? You have the target as some radius, and classically any impact parameter that's kind of bigger than the radius will just have the particle just whiz on by. But quantum mechanically, that's not what happens. You actually have to solve the Schrodinger equation and figure out what the wave function is. And in some sense, I guess the intuition of this is that you do get quantum mechanical contributions to scattering that kind of come from, well, basically impact parameters that are larger than the target kind of radius. If you think about it in terms of hard sphere scattering or something like that. So yeah, so that's an important thing. This is an important intuitive kind of calculation that shows you that quantum mechanically you can get quite a different answer than what you would expect classically. Any questions about that? No? It's all clear? Okay, so what we're gonna do next is talk about what happens at low energies. So small impact parameters. Yeah, so small angular momenta. It's just small impact parameters and small k. And in that case, you know, the kinds of solutions we'll be worried about quantum mechanically are the ones that, you know, have small l. So again, it's all kind of related. So it's small k. It depends on which things you hold fixed, but we'll look at low energy scattering in the sense that we'll look at solutions to the Schrodinger equation at small l, or l equals 0. And that's called S wave scattering because the l equals 0 mode is called the S mode, as I mentioned. L equals 1 is P mode. So this is sort of the topic of S wave scattering. And S wave scattering is important because it's the closest you get to just like 1D scattering. This is very simple because your Schrodinger equation then just reduces to a 1D Schrodinger equation. There's no longer any of that angular momentum terms in there. You just, you know, L equals 0. Spherical harmonic is just a constant. So everything just reduces to the radial coordinate. and it's pretty simple. You can solve it as you would a 1D problem. So again, whenever you hear the term S-wave scattering, just means the solution is dominated by the L equals 0 mode. In this case, it's convenient to parameterize the phase shift. So now there's only one phase shift. Instead of delta L of K, this is just one of them because there's just one L mode. And there's a single phase shift, and it's convenient to parameterize it by a length. It's nice to define something called the scattering length. Which is defined as the minus the limit as K goes to 0 of the phase shift associated with that L equals 0 mode divided by K. And obviously it's 1 over a wave vector, so the units are units of length. And basically, recall that, again, the full solution, the scattering cross-section, scattering amplitude, the solution itself, right, is entirely determined by the phase shifts. If you know the phase shifts, then you know everything there is to know about the scattering solution. Like that's all the information you need. So for S-wave scattering, if you're only considering one mode, that means you only need one parameter to fully specify the solution to the scattering problem, right? You just need a single phase shift, or equivalently a single scattering length. Because we're gonna, of course, that's not quite true because the thing depends on K, the incoming momentum. But at least if you're only worried about sort of what happens in the low momentum limit where you send K to 0, the incoming momentum, then in that case, everything really is kind of determined by just the scattering length, as we'll see. But we'll see all that in a moment. So because we're going to do an example and sort of see how it works. So let's do an example, an easy one, which is the spherical well. So our potential will just be minus V naught in some range, and then 0 otherwise. So the idea is you have a potential that's sort of like this. And remember, this is like at the center of your coordinate system. It's a potential well, and you're sending in a plane wave from some direction into the origin, and then watching stuff scatter out. And of course, we're sending stuff in at some positive energy. So our energy is somewhere over here, just some kinetic energy. So let's see what happens. The Schrodinger equation in this case is really quite simple because, again, we have no L terms. It's just du dr squared is equal to minus 2m over h bar squared E minus V times U. This is just the usual Schrodinger equation in spherical coordinates. And again, it's just the L equals 0. And this is just like a 1D Schrodinger equation. It's not any different. And for us, for this kind of piecewise constant thing, we know how to solve it. It's just, sines and cosines for U here. And of course, the only other thing to remember is that at the origin, remember that the wave function itself, the psi of r, is proportional to u over r. So there's an extra boundary condition on u. It's that at u at r equals 0, has to vanish. And so then, you know, these two things combined, we just write down what the solutions are. So U of R is equal to, it normally would be sines and cosines, but because of this boundary condition, when R is less than big R, you just get the sine. So it's a D, there's some coefficient D to be determined, sine of K prime R, and then far away from the target, you'll have sines and cosines. But remember, we're trying to determine the phase shifts. So it's best to write the solution as not sines and cosines, but as a sine KR plus delta. Because this is exactly the right form, right? We have the incoming momentum here because far away from the target, away from the potential, you just have the kinetic energy that you came in with, right? If there's no potential there, it's just the kinetic energy. So that has wave vector K times R plus this phase shift, and the phase shift is what, you know, gives you all the scattering properties. And then there's, of course, you know, the K prime where, you know, we can, it's just the same as we did before for 1D scattering. It's just, this is square root of 2m E plus V naught over H bar squared, because in that potential well region, you pick up some potential energy. And outside of it, it's just whatever the incoming kinetic energy is. It's just the usual thing, solving a square well. Okay, so we know how to do this, right? It's the usual thing at the boundary between the two regions here. R is less than big R and R is bigger than big R. We just apply continuity, right? And in particular, continuity of the logarithmic derivative. And if we apply that, we take some derivatives here. We get d k prime cosine k prime r divided by d sine k prime r. That's on the left. On the right, we have c k cosine kr plus delta over sine kr plus delta. See, and as usual, the coefficients cancel. This is why you take the logarithmic derivative, because you don't, again, you don't really care about the coefficients out front. The coefficients out front has something to do with just the amount of incoming stuff that you put in to scatter. It's the incoming amplitude. You're worried about the phase shifts. That's what tells you what the effect of the scattering is. So it's nice to just immediately do the match the continuity of that. But of course, you can do both. I mean, you can definitely do both. Do continuity of the logarithmic derivative and the wave function, and sort of solve everything. You'll have one unknown left over. You know, so you have three unknowns, right? You have two equations, continuity of derivative and the thing. So you can solve for two of these unknowns. The last unknown is just the incoming momentum. So that's, or the incoming amplitude. So that you can do it all that, but it's much faster if you just want to extract the phase shifts to calculate the logarithmic derivative, because then those other coefficients cancel and you get a formula for the phase shifts, that k prime times the cotangent of k prime r is equal to k times the cotangent of kr plus delta. now you have everything you need to know to solve for delta. And of course, this is like a transcendental equation. It's hard to, you can't really invert this. It's hard to, well, it's not, it's, yeah, no, it's fine. You could solve for delta. You just pull the k over here, take the inverse, the cotangent, but it's nice to think about this in the small k limit, because we'll be able to identify the scattering length in the small k limit. But before I do that, it's also convenient to see that the solution has in it those S matrix elements. So we can expand the cotangents in terms of complex exponentials, and you get the following. Get the ratio of the sums and the differences between these guys. On one side, there's a factor of 2i, but it sort of cancels on both sides. And here you have e to the ikr plus I delta. So you see in here, what shows up are the e to the I deltas. And in fact, we can multiply and divide by e to the I delta. And then this becomes k times s, the scattering, the S matrix element for that L equals 0 mode, just e to the 2I delta. And you have s e to the ikr minus, or plus e to the minus ikr over s e to the ikr minus e to the minus ikr. And we can now actually solve this for S to get the S matrix contribution to the L equals 0 mode. So you can solve it. This is just some algebra, right? You put all the S's on one side and then divide. And what you end up finding is it's e to the minus 2ikr. And you can put the exponentials back together and you'll get cosine I k over k prime sine, and on the top and on the bottom you'll get so that's the S matrix for the scattering there. The S matrix for the L equals 0 mode. We'll talk more about the S matrix later, but again, for now, just remember that this S is what comes into the general solution that we have for the wave function. So now, once we have S, we sort of have the solution. These are the S, right? And this is the wave function for the scattering solution. So that's worthwhile to keep in mind. And I also mentioned that it's nice to think about what the scattering length is, which is the phase shift divided by the incoming momentum as you send k to 0. And we could also calculate that to get some intuition for what kind of scattering length we would get for this square well potential, for this kind of spherical well potential. Again, so the idea here is we're looking at low energy scattering. So that when you say S wave, it means L equals 0. But more than that, it also corresponds to what happens in the low energy limit. So concurrently with that, you set L equal to 0, you also make the incoming momentum small. And in the limit of all those, you'll just get something that depends on a single parameter, which is the scattering length. So, but in principle, if you just look at the L equals 0 mode, there's still some K dependence. So that's kind of the idea of what's going on here. And we're just doing this example to get some intuition about what the scattering length would be. This would be the sort of 0 momentum limit of the phase shift. And we're also I'm just showing you how you calculate, in general, the phase shift as a function of K, for some example. So that's kind of what we're doing here. And along the way, we solve for this S, which goes into the full solution for the wave function. But let's look at what happens now at small k. At small k, well, k prime, right, is going to be, remember I still have the k prime somewhere here. Right? The k prime, right, is related to E plus V naught. So if k is small, and small compared to like the depth of the potential well, then this energy is going to be small, right? The energy is going to be small compared to the potential well depth. So as you send k to 0, we're just imagining the energy being real small compared to the depth of this potential well. In that case, k prime is approximately equal to k naught, which we just define as 2m v naught over h bar squared. And so then things are a little bit easier in terms of the solutions, because you just have, if you go back to the solution here, right, this is a little bit easier now. This is going to be k, and we can we can flip the cotangent is 1 over the tangent, so we can sort of flip these guys around. So then k gets multiplied by the tangent of this guy. So k times the tangent of k naught r, right, because this is k prime, it's approximately equal to k naught, is equal to k naught times tangent of kr plus a delta. And now, if k is really small, then we can Taylor expand this tangent function. And what we'll get, and that's assuming that delta is small, but we'll see that it is. We'll get k naught times kr plus delta. This is a Taylor series of the tangent, just keeping the first term. So now we can solve for delta, right? It's pretty straightforward. The delta is equal to k over k naught times tangent of k naught r, and then it's minus kr. So if we look here, as k goes to 0, right, the delta vanishes. So that's good. It's consistent with our Taylor series thing. And moreover, you see when we divide by k, we actually just get a number. So in this case, the limit is really quite easy for the scattering length. Again, remember it's minus the limit as k goes to 0 of delta over k, which in this case is going to be well, it's r minus 1 over k naught tangent of k naught r. And it's nice to rewrite this as r 1 minus 1 over k naught r tangent of k naught r. So this is a very cool thing because you see it's not really that trivial of a dependence on the potential well depth. It's proportional to r. So if we have a very shallow potential, well, let's plot this thing and see what it looks like. So the plot of so as a function of x, which is k naught r, if we were to plot the scattering length divided by r, what happens here? So at small k naught r, at small x, you'll get basically an x over x, which is 1, right? Because tangent of small is it's like sine of x over x. So that approaches 1. So this actually starts out at 0. It goes negative. And then whenever this is at pi over 2, the tangent function blows up. So when you're at pi over 2, you get an asymptote where the scattering length actually goes negative and diverges. And then after that point, it pops back up again, and we get this kind of thing, right? So that's the plot of this scattering wave function, or the scattering length. Now, what do you guys think happens at this point? Why would the scattering length diverge there, and what could it represent physically?
Does it just mean that it's not scattering, so it's bound?
Yeah, exactly. Or it means that it's sort of, yeah, it means that it's bound. So it means that really it scatters a lot in some sense, because if you send in, imagine what's happening, right? We're sending in a particle at very low energies into this spherical well. And you're right, at this point, this corresponds to a bound state for the potential. So when x is equal to this special value, the spherical well potential develops a bound state, right? As you make k naught, which is just the potential well depth, bigger, right? At some point, if it's very shallow, then it has no bound state. But at some point, it gets deep enough that it develops a bound state. And so at that point, that's exactly right. That's where this a over r diverges, becomes negative, and goes to negative infinity. At that point, as soon as the bound state develops, right, if you send in a particle in there, it might get stuck, and then it might take it might get stuck in the bound state, and then it can become trapped. So it becomes the spherical well potential becomes like a very like a nasty trap for the particle. And so it's not that it doesn't scatter, it's like it gets scattered a lot. It becomes, extremely, it can become trapped inside the potential. So we can see that's, so let me then show you what happens to what you would actually measure, which is something like the scattering cross section, right? If we look at the limit as k and l go to 0 of the scattering cross section coming from the L equals 0 mode, remember that this we derived from the partial wave expansion that this is 4 pi over k squared sine squared delta L. If delta is small, which it is as we send k to 0, this is of course going to be equal to limit as k goes to 0. If L is 0 here, it's 4 pi k squared delta squared, but this is nothing but, right, the scattering length squared. So you see you'll get actually a lot more scattering, but remember this, so this is, what's the scattering cross section, right? It's the amount of area that the incoming particle sees as it comes into the target. And it'll see a whole lot of area if there's a bound state, because the particle that's coming in will get trapped at this point. This is when you just developed a bound state, so the energy of that bound state, right, is just a little bit below 0, and you're sending a particle in at basically 0 energy. So if you send anything like that in, it's guaranteed to get trapped, and that's why you get this kind of divergence in the scattering length. And its sign changes across the transition. So so that's the intuition for the spherical well, is that the scattering length, and that's why the scattering length is an interesting quantity, right? Because it gives you a signature. You can use scattering essentially to probe whether or not your potential has any bound states in it. If you measure the scattering length and you find that it's negative and large, that means your potential is just shallow enough that it doesn't quite have a bound state. If conversely your scattering length is large and positive, that means you have just developed a bound state in your potential. So yeah, and in the book, if you read Belak, he has sort of more intuitive pictures of what these various situations look like. So again, what happens if the scattering length is large and positive, if your potential has a kind of well shape, then there's a bound state here, and so your radial wave function, it'll have a portion of it that kind of has a bound state component. So this is the form of your U of R in that case. Conversely, if your potential is too shallow for a bound state, kind of make it more shallow here, and your scattering length is negative, then there is no bound state, but it's like almost there. And what your radial wave functions look like in that case, so this has to go to 0 here. What your radial functions look like in this case are sort of like this, and they come in sharply here. There's a lot of density sort of inside the well, because it's almost trying to form this bound state. It's almost trying to turn over like this and make a little bound state shape, but it can't quite do it. And so the scattering length in some sense tells you about this extrapolation length. If this were to continue going down to 0 linearly instead of sort of swooping down here to 0 right away to satisfy the boundary condition at the origin, this length here of this extrapolation would be, that's the negative scattering length. So you can sort of see that as you make a bump in your wave function shape, that would correspond to the wave function for the bound state, right? If you can't quite make a bound state, it'll try to make that bump and not quite get there. And then that kind of slope associated with that top of that bump kind of almost forming, it tells you about this negative scattering length. It also makes sense that as this wave function turns over, becomes flat, this A will go off to negative infinity. And then as the whole thing just turns over, the positive scattering length tells you about the kind of size of the wave function corresponding to that bound state in the well. So that's very kind of hand-wavy intuition, but it's nice intuition. And again, if you want to get it all right, I guess the best way to do it would just be to do this example right, and then stick in, go back to the solution for the wave function for the u's and actually plot the wave function and see how it changes as a function of k naught r here, because that lets you tune across all these different regimes. And the other thing is, the other kind of situation is if you have a potential barrier for scattering, right? And if you have a potential barrier, if we imagine the wave function, what does that look like? Well, it'll, as soon as it hits the barrier, if the energy is sort of below somewhere, if you're sending in at low energies, right? If this is E, as soon as it hits the wave function hits the potential, it'll start to exponentially decay, right, into the, it'll just exponentially decay to zero there, away, because you're in a classically forbidden region as soon as you're inside the barrier. And in that case, the scattering length is kind of, it's related to the distance between where the potential drops off to zero and the origin. It's kind of, so, and I'll show you what that means in a moment when we do an infinite potential barrier. So for an infinite potential barrier, you would hope that the scattering length is just equal to the size of the barrier. And well, it is, so I can show you that. So for infinite potential barrier, so again, so these are different situations for different potentials, right? For S-wave scattering, you either have some kind of well or you have some kind of bump. And these pictures here just show you intuitively what the scattering length corresponds to in all these situations. Remember, the scattering length has to do with what the scattering looks like at very low incoming momentum. And that's just the intuition. So if you have a well, then the scattering tells you something about whether or not you have a bound state there. And each time you pick up a bound state, the scattering length goes from negative large values to positive large values. And that corresponds to the change in the shape of the radial wave function. And otherwise, if you have a barrier, then the scattering length tells you something about the distance into the barrier you have to go before you actually start picking up some positive contributions to the radial wave function, some non-zero contributions. But we can show that immediately for the infinite well. So if we do infinite well, or infinite, sorry, barrier. We do the infinite barrier, meaning we take our potential to just shoot up to infinity at some location A. Well, it's easy to solve this problem because we know we just have sines and cosines, and we just have to make sure that our radial wave function here vanishes when little r is less than, oh, let's make this big R just for convenience. So the step function, it vanishes when little r is less than big R. Otherwise, there's some amplitude and there's a sign kr plus delta. And so then we just have to make sure that that the sign here vanishes when little r is equal to big R, satisfy the boundary condition. So we have to make sure that k times r plus delta is equal to some multiple of pi. Those are the only constraints, and at small k, the relevant solution is the one that has the smallest phase shift, and so in this case it's really the n=0 solution, and in that case delta is just minus kr. And then it's really quite easy. The scattering length again is minus the limit as k goes to 0 of delta over k. So it's just r. So as promised, the scattering length is just equal to the size of the barrier. This is hard sphere scattering, right? This is not allowing your particle to get any closer than big R to the origin. And okay, and let's just make sure that we have it right, that when we calculate, let's calculate the scattering cross section in that limit, right? What's that? Well, it's just 4 pi a squared. We already saw that, so it's 4 pi r squared. Really weird, right? It means that, so infinite barrier, I should just say, you could also say hard sphere. It's really weird because classically we would have expected for hard sphere scattering to just get the area of the sphere, which is pi r squared. But here we get 4 times as much scattering, 4 pi r squared. Weird. I mean, the quantum mechanical answer is 4 times larger than the classical one. And it's confusing, but you shouldn't be that confused because remember, this is S-wave scattering at low momentum, at low energies, when quantum mechanical effects are going to be most important. So yeah, so those are the major examples. Hopefully you're starting to get some intuition of what these quantities represent. But again, remember, from my point of view, all we're doing is just solving the Schrodinger equation with various boundary conditions. But in this scattering case, it's sort of nice to connect it back to some classical notions of like scattering particles off of hard sphere targets, and seeing that you get pretty dramatically different results quantum mechanically, especially at low energies when the quantum mechanical effects sort of are most pronounced. I think this is probably one of the more dramatic calculations, right? We showed that for a hard sphere, the low energy scattering, your cross section, the total amount that the incoming particle sees at low energy is actually 4 times the projected area of the hard sphere. Just kind of something to think about, I guess. And of course, it's kind of funny. It's such a kind of simple result, but then you have to recognize that at high energies, right, we somehow must be able to recover the classical result, right? So that's kind of cool too, to think about how you would recover the classical result at high energies. It should just eventually just get back out classical hard sphere scattering, which should give you a pi r squared instead. Okay, any questions about that? I'm going slowly this class because it's sort of more conceptual. Hopefully it's sort of absorbing somewhat. Okay, so this was all kind of the small k limit. You can also do S-wave scattering for non-zero k. You could sort of allow your incoming momentum to be a bit bigger, and then you could just continue in the Taylor series. You can continue in your Taylor series for like the phase shift, for instance. So so we can think about that, and so to sort of 0th order in K. So again, we're in the small K limit. So if we think about, and again, this tells you everything about scattering. Remember, that's the thing that just determines everything about your solution of Schrodinger equation. So again, what we've been looking at just now is just when we approximate this by minus K times the scattering length. That's kind of the 0th order term. But you can go higher, you can go to higher order terms. It's not obvious that you can Taylor series the phase shift. And as it turns out, what you want to Taylor series is not quite delta, but it's actually K times cotangent of delta. This is, you can Taylor series this. And moreover, you can show that it's analytic in K squared. Maybe I'll show that in recitation at some point. But this we can expand. And the first term will be minus 1 over A. That just comes from this. And the second term will be something that's of order K squared. And so now you can use this as a kind of approximation to your phase shift, right? So to first order in small k, you just say, well, the phase shift is linear in k. It's minus k times the scattering length. If you want to do a little bit better, you would have that term plus another term. And for technical reasons, what you want to do is Taylor series this quantity instead of delta k. And this quantity is, you can show, is an analytic function of k squared. So you can Taylor series it in powers of k squared. Just so again, this is the next term would be of order k fourth. Maybe I'll show that later, but it's a little bit of a technical point. And this thing is called this R naught is something called the effective range. And it has dimensions of length, just as the scattering length does. And just so you know, if you have a phase shift that's described by a scattering length and this effective range, the associated scattering amplitude for S-wave scattering is, and again, remember it's related to the phase shift as follows. You can also write this as 1 over k times the cotangent of delta minus I, as it turns out. And this, if we plug in for that, it's minus A over 1 plus IKA minus 1/2 R naught AK squared. So, and you can use the scattering amplitude to calculate the cross sections if you wanted. So, and notice that you can do this, this is independent of the potential. This is what I want to emphasize. In S-wave scattering, if you start perturbing away from k equals 0, you just need a couple parameters to fully specify your scattering problem. To lowest order, you just need the scattering length. That tells you everything. If you want to do a little bit better and sort of see what happens at higher momenta, larger momentum, then you could introduce this effective range parameter. And then you can parameterize everything about your scattering problem with these two lengths, the effective range and the scattering amplitude. And I think generally this is all you pretty much ever need for kind of low energy scattering problems. So yeah, so that's kind of interesting. Belek does a pretty good job in describing this in more detail. There's problems in the end of the chapter that kind of go over the analytic properties that actually help explain why you want a Taylor series this quantity instead of just delta. But maybe I'll do that in recitation as a sort of example problem. Yeah, so that's S-wave scattering. Again, it's important to kind of keep track of what's going on. S-wave means only the L equals 0 modes. And then within that approximation, you can look at, you're looking at small incoming momentum, but there's various degrees of that. You can look at the K goes to 0 limit. That's when you get that scattering length. Otherwise, you might want to pick up higher order terms in your Taylor series for this quantity, and you can pick out another parameter. It's like the second order term, which is the effective range term. So yeah, any questions about that? If not, this is a pretty decent place to stop. What we'll do next is go back to our general solution and talk more about this S. See this S we had here, if you look at it, what we'll find is, so the form of S is always, for elastic problems where energy is conserved, it always has the form, remember all the way back at the beginning of class, S has this form of e to the 2I delta. What we'll see is that when you have inelastic scattering, and you might lose some, you'll lose some basically probability. And what will happen is S can actually be smaller than, the magnitude of S can be smaller than 1. It's not just a simple phase. And the amount that it's smaller than 1 actually tells you something about how much was lost during that inelastic process. So that's what we'll talk about, inelastic scattering and the optical theorem. You see, if S is less, then there's sort of less of the outgoing, right? There's less of the outgoing spherical wave. That means some of the incoming stuff must have gotten trapped somewhere in some inelastic process where you come in and the stuff that comes out doesn't match the stuff that came in. So there must have been some kind of loss of probability due to inelastic scattering. That's what we'll talk about next time. But that's it for today. Sort of going,